Good morning. You're welcome to this top-quark session of our workshop. And today we will have this morning two talks. One on the experimental perspective by Philipp Roloff, followed by Massimiliano Grazzini on theory aspects. And we start with Philipp from CERN. And please, Philipp.
Yeah, good morning. I hope you can hear me.
Yes.
Okay, very good. Yeah, thank you very much for the invitation. As said, I'm going to give an experimental perspective on top physics at future colliders. Just to remind ourselves, here on the second slide, I collected the studies of high energy plus and minus colliders. Of course, there are the studies for the linear colliders, CLIC and ILC. So CLIC is between 380 GeV and 3 TeV, and then the ILC, of course, between 250 and 500 GeV, with the option to extend to 1 TeV. Of course, there's the FCC-hh study at CERN, which would operate between the Z-pole and 365 GeV, which is a bit above the TT bar production threshold. And then a bit less relevant for this presentation, of course, there's also the CEPC study in China. Of course, there's also ideas for future high energy proton-proton colliders. Of course, the simplest step would be to install new magnets in the LHC ring, which would then lead to the high energy LHC, where we here assume 27 TeV center of mass energy. And then, of course, the FCC-hh with a circumference of 98 kilometers would provide us the ultimate energy of 100 TeV proton collisions. And of course, all the details on these studies were given in the presentation on Monday by Stefan. So just for reference, I put here the table from the European Strategy briefing book summarizing the proton collider studies, the plus and minus collider studies, where you also see the details on the different energy stages. There are also some studies for EP colliders, which will become relevant in the last part of my talk. And then in the bottom left, you see the timescales of these colliders, how they evolve from the time of first data taking. There are even more advanced ideas, of course. We all heard about this already on Monday a bit. So of course, there's now a renewed interest in the muon collider. And then of course, there's also E plus E minus collider studies at even higher energies using advanced technology. I want to just have a few slides on the detector concepts because I will later then mention where these are relevant for top physics. So of course, the ILC detector concepts are really designed for particle flow. So they are equipped with high granular calorimeters inside the magnets. And at the same time, they have low mass trackers to reduce interactions and conversions before the calorimeters. And then this leads to the designs shown in the pictures here. So there's the ILD concept, which has a TPC with silicon envelope with a large radius and a B field of 3.5 Tesla. Although they recently also tried a different option with a stronger field and a somewhat smaller radius. And then there's the SID concept, where the main difference is that they go for full silicon tracking with a smaller radius compensated by a higher B field. Then here we have the click detector concept, which is also optimized for particle flow. We have a silicon tracking with 1.5 meter radius, and then of course a deeper HL compared to the other E plus E minus options due to the higher energies. One particular aspect here is that we need precise timing. So it's assumed to have 10 nanosecond precision on individual hits in the tracking and 1 nanosecond precision for hits in the calorimeter. And this is needed to mitigate the beam-induced background, which otherwise would affect our physics. So you actually can see this here in a E plus E minus to TT bar event at 3 TeV. On the left side, just with all the background particles. And then when we apply the timing cuts, you see that we clean this effect nicely up, and we can basically see the two boosted tops by eye. Of course, there are also designs for the FCC-hh studies. One is derived from the click detector, which I've shown on the previous slide. So due to the fact that at the circular collider, you have a limit on the luminosity, a limit from the luminosity goal on the magnetic field, which is 2 Tesla. You want to compensate this by a larger tracker to keep the momentum resolution good. So the larger tracker here is seen in the picture. And then at the same time, of course, you have lower overall jet energies. So on the other hand, you can keep the H-cal less deep, as for example, in the click detector. On the right side, you see the idea concept, which tries some new technologies. So this is also using a 2 Tesla field, but it's equipped with a drift chamber for PID with a similar radius of 2 meters, and then dual readout calorimetry outside of a very thin solenoid. And then it's also equipped with an instrumented return yoke. Finally, there is an FCC-hh detector concept. So here I'm showing you the reference detector, which was presented in the CDR. There's no full simulation of this yet, but it gives us a good idea how such a detector could look like. So this is a 4 Tesla field, 10 meter diameter. And this reference detector is based on full silicon tracking and then liquid argon calorimetry everywhere except for the barrel H-cal, which assumes scintillators with iron absorber. So if we just compare those to Atlas and CMS, you see that the forward calorimeters are moved out to reduce the radiation load and increase the granularity. And you also see that we basically have this big radiation shield here, which is needed to stop neutrons escaping to the cavern and the muon system. So those are the detectors which are basically assumed for the studies which I'm going to present in this talk. And I have structured the discussion of top physics as you see here on this slide. So of course we have detailed studies of top-quark pair production in the plus and minus colliders, and those are based a lot on full simulations of the detectors you have seen on the previous slides. So I'm going to review the status and the recent developments on the mass, on the electroweak couplings, and also on some processes and high energies. I will then show some highlights for the FCC-hh, and then the last part of the talk will be a discussion on flavor changing neutral current effects, where I'll discuss all the colliders together, and that will be the last part. But let's start with the pair production in the plus and minus. So this is just a plot of the cross section for various processes as a function of the plus and minus center of mass energy up to 3 TeV. And of course, we have pair production, which has a threshold at 2 times the top mass. And then we have a region, let's say, between 365 and 500 GeV, which is near the maximum and provides us, in terms of overall statistics, the largest event samples, which is, for example, relevant for rare decays. Then, of course, we have TT bar production associated with the Higgs. This has a maximum at around 800 GeV. And then finally, of course, we can also produce the top pair in vector boson fusion. Of course, this profits from the highest energies, and you see that the cross-section rises roughly logarithmically with the center of mass energy. So let me go through what we can do with all these processes. So of course, the first question is the top mass. So here you just see a bit on the current status and near-term future. So on the left, we see a plot comparing direct limits to the indirect constraints from the electrophic fit. And you see actually that the top and also the W mass, of course, are important ingredients to the overall understanding of the standard model. On the right, there are some extrapolations from CMS, unfortunately already a few years old, showing how the knowledge of the uncertainty on the top mass is expected to evolve in the high luminosity LHC area, comparing the various measurements. Now the question is how well we can improve on this at the plus and minus machine. And I'm going to review different techniques, starting with the threshold scan. Of course, at higher energies, we can also directly reconstruct the top pairs. And then relatively recently, people have also looked at radiative events. So let's start with the threshold, which really has been looked at since a long time. But here just a brief reminder. So what is nice is that we do have precise theoretical calculations of the cross-sectional threshold region, which are based on well-defined mass schemes. So we can use these theory predictions to extract the mass in the threshold region. Of course, this is sensitive to various top-quark properties. So in the left plot, you see basically how the threshold region as a function of the center of mass energy looks. And then you see how the shape of this distribution roughly depends on various parameters. So the mass mainly guides the position of the flank towards the 1s peak, and then the peak itself is also guided by the width. And then above the threshold, the cross-section is also guided by alpha S and the top-Yukawa coupling. So unfortunately, the distribution which we would measure in the colliders would not only depend on these quantities, but of course there are also influences from collider parameters and from ISR. So this you see illustrated in the right plot, where you basically have the black line as the theory prediction, and then if you add initial state radiation, this gets smeared out, so you end up with the green. If you would just include the Beamstrahlung effect, for this is, for example, for the ILC, you won't end up with the blue. And then if you have both effects, you end up with the red curve. So in real life, the distribution is not as nice, but we can still extract what we want to extract from it, of course. So there have been very detailed studies of this. Here's just an example again for the ILC. So what you would do is basically you would do a couple of cross-section measurements in the region of this threshold effect, and then use this to extract the mass and various other parameters at the same time. What you see on the right side is again a more detailed study of what we have illustrated before. So it's basically the variation of the curve when we modify either the mass or the width or alpha S. And you basically see what was illustrated before, that basically the mass is influencing here this part of the turn on, and then the Yukawa coupling will be constrained up here, and then the width is more here and here. So there have been very detailed studies on propagating the current knowledge of the, let's say, various parametric uncertainties and also theory uncertainties on the precision with which we can extract the top mass. So here you see a breakdown of these various influences, and you see actually that the current knowledge would limit the precision much more than actually the statistical error. So there's certainly some room for improvement there. There's also a very recent study which actually has looked at how we can optimize how one would do such a threshold scan. So in the left, you see the baseline scenario. So this is very similar to what we have discussed on the previous slide, where people just assume you would take 10 data points with the same luminosity at each point. And what people did was basically a generic search algorithm which tried many different choices for making such a threshold scan, keeping the overall luminosity which you would spend at the same. And what comes out is that actually, for example, if you want to measure the mass and the width, the best choice is actually having something like 4 or 5 points, which are really focused here on this turn-on part of the curve. And you see here on the right, basically a comparison how this improves the top mass measurement. So if we take, for example, FCC-hh, you have the blue solid curve. If you would do the threshold scan with 10 equidistant points, if you would manage to go to something like this optimized scenario, you would get a 25% better statistical precision on the mass, and you would end up with this dashed curve here, which shows you how the precision evolves with the luminosity. you see that there's some difference actually between the different colliders on the precision of the mass, and this is basically due to the different luminosity spectra at the different facilities. So you see this on the bottom right, that basically, especially at the linear colliders, you have this tail in the distributions from Beamstrahlung, and this effectively reduces the luminosity you have for the threshold scan, which leads to a somewhat larger statistical error. So this is, of course, the most well-studied way of extracting top mass, and it gives you a well-defined measurement. Of course, there are other possibilities. So the most obvious one is just to look in the continuum. This is an example for click at 380 GeV, where you would just reconstruct the hadronic invariant mass either in fully hadronic TT-bar events or in semi-leptonic TT-bar events. You can actually suppress the backgrounds very well, as you see in the distributions on the bottom. And then one could just do a template fit to extract the top mass. This would give a statistical precision in the order of 30 to 40 MeV. Of course, this would be very, very challenging in terms of systematics. So it would require excellent knowledge of the BJet and the jet energy scale. So one could envision, for example, a short calibration run each year on the Z-pole, which would give you sufficient calibration of these effects. But also, of course, the interpretation of the measurement would be much more difficult than what you could achieve in the threshold. Somewhat of a mixture of the two approaches is to use radiative events, which would allow you to extract the top mass in a well-defined scheme above the threshold. So the idea here is to measure the effective center of mass energy, and then in the effective center of mass energy, you see a turn-on curve, which really looks like the threshold curve, which we have seen before. And then you can again use precision calculations in a well-defined mass scheme and fold those with the luminosity spectra and then do a fit to these distributions. You see here what you get in terms of precision. So the best measurement you get if you are not too far away from the threshold. So at click, you could achieve something like 110 MeV overall precision, and at ILC at 500 GeV, 150 MeV. So this is not as precise as a threshold scan, but it's a nice complementary measurement. It would also actually allow you to have a 5 sigma evidence for the running of the top quark mass in a single experiment. So this is a study for the ILC. You basically see the dependence of the MSR mass from the scale parameter, and you see that we actually do see a running in a single experiment, which is quite a nice additional result which you could get from the radiative events. So this is basically all I had on the top quark mass. So I would like to speak about the electroweak couplings of the top next. So of course, the top pairs in plus and minus are produced via Z or gamma. And then of course, we can parameterize the coupling in the most simple approach with form factors. And of course, we can use TT-bar production above threshold to constrain these form factors. You have to find some way to disentangle the couplings to the photon and to the Z. At the linear colliders, you can do this using beam polarization. So the observables which you use are the cross-section for different beam polarization configurations and the forward-backward asymmetry. Here just some examples of the reconstructed polar angle distribution in semi-leptonic events for two different polarization combinations which would go into such an extraction. You can, of course, also use the properties of the final state leptons from the W decays where the spin propagation, where the spin information is propagated. So you can also extract the form factors using kinematic distributions of the final state leptons. So you can actually also extract the form factors at a circular collider without polarization, and of course these both aspects are complementary. Here just a comparison of what you can achieve in a plus and minus machine compared to the latest extrapolations combining LEP and HL-LHC. So those are the red bars, and then we can compare this to some ILC and FCC-hh studies in blue and green. And you see that lepton colliders have a significant improvement by 1 or 2 orders of magnitude. And then you can even combine different techniques further to improve this. So what about higher energies? Of course, for click, we studied energies up to 3 TeV. And as I showed in the beginning, we have these very fine-grained calorimeters. So in principle, the E plus E minus detectors and the relatively clean environmental conditions are ideal to study jet substructures. So this is not only for top physics, but actually also for many other applications. So the first thing we tried is basically to use techniques developed for the LHC, so reclustering and the Johns Hopkins top tagger on boosted hadronic top-quark decays at click. And it actually works very well. So you basically, with the way we tuned the algorithms, you basically see that we basically top tag all the top candidates in semi-leptonic events. And then we can basically reconstruct, for example, again, the forward-backward asymmetry at 3 TeV using these boosted techniques. And then you see here for 2 different polarization configurations, we can also measure AFB in the boosted regime. This is, for example, at 3 TeV. Now, instead of speaking of form factors again, of course, we can also do an EFT analysis of E plus E minus to TT bar production. So the first example I will give is an EFT analysis of the full click program. So this is combining the 3 energy stages, 380 GeV, 1.4 TeV, and 3 TeV. You see here the sensitivities on a set of operators relevant for TT bar production. And if we would just use the cross-section and the forward-backward asymmetry, as we have discussed on the previous slides, we would basically end up with the limits shown by the orange bars. There's further improvement possible if you just not only use the cross-section and forward-backward asymmetry, but if we actually use so-called statistically optimal observables, which actually make use of differential BW distributions instead of just cross-section and forward-backward asymmetry. And then this illustrates you the type of improvement you would get, because with the statistically optimal observables, we would end up with the blue error bars. And then, of course, we already see here, and this will come back many, many times, that the highest energies really are very good to constrain the 4 fermion operators. Similar EFT analysis has been performed for all the colliders. So this is from a different publication, and it shows you the expected precisions on a similar set of operators, comparing a scenario which is roughly similar to FCC-hh, a scenario which is roughly similar to ILC with a 1 TeV stage, and then the click scenario. And you see again that, of course, higher energy and polarization significantly enhance the reach. And this is especially true for the 4 fermion effects. So, of course, this kind of EFT analysis are super useful to compare different collider options. We can also use the limits, which we have seen on the previous slides. This is for click. And illustrate the reach on top-quark compositeness. So what you see in these 2 plots are compositeness scale and coupling exclusion for 2 benchmark scenarios, so-called partial compositeness and total TR compositeness. And then the yellow areas basically show you the limits which can be obtained from TT bar production. So this is using the operators, which we have seen on the previous slides, as an input. And for comparison, it actually also shows TTH, which we will discuss a bit later. And we can see that we would have, even in the worst case, discovery reach at 5 sigma for compositeness scales up to 7 or 8 TeV. So as I already said, of course, beyond TT bar production, there are other processes which become interesting at high energies. So of course, the most well-studied one of those is E plus E minus 2 TT-Higgs, which has a maximum at around 800 GeV. It can already be measured at a bit above 500 GeV, and then it remains interesting up to around 1.5 TeV or so. In E plus E minus, we are really limited by statistics. You see the cross sections are small. So the most important final states are the ones where the Higgs decays to BB bar, because all the other ones just have very small statistics. And each of them, basically the semi-leptonic or the fully hadronic decay of the top provides similar sensitivity. If we combine the two and we look at various projections for click and ILC, so one can typically get a direct extraction of the TT-Higgs coupling in the order between 2 and 3%, which is a bit better than what you can get from the high-LHC. What will be very interesting if you go to even higher energies is actually TT-Higgs production in vector boson fusion. For example, for the muon collider, this will be a very interesting process if you go to much higher energies. Now, beyond the cross-section and the top-Yukawa coupling, we can of course also look for sensitivity to CP mixing in the TT-Higgs coupling. So we just use the parametrization which you see here in the plot. And then you see here the limit which one can set on the mixing angle for the CP-odd contribution. As I said before, what you see in the dashed blue and green lines is from the semi-leptonic and hadronic final states if you just use the cross-section. And as I said before, the precision on the cross-section is relatively similar. If you combine the two, we basically end up with the red line, but you can then, of course, improve this further if you use differential information. So the points in magenta show you basically what happens if you combine the cross-section with the so-called up-down asymmetry. And then depending on the value of the mixing angle, you actually get a significant improvement beyond what you just get from the cross-sections alone. There's one more process which we had a brief look at, and this is TT bar production in WW fusion. So here you see that, of course, this can affect EFT operators, especially in the region of high invariant mass of the two top quarks. This is basically a generator level study, and more detailed simulation is very clearly needed. You see here an illustration of single operator sensitivities, which already hints that a combination with TT bar, as we have seen before in a more global fit, could be beneficial. And then, of course, this type of process will be very interesting if you go to even higher energies, let's say the muon collider again. So there's some interesting work to be done in the future here. So this was kind of my review of TT bar production in E plus E minus. I want to flash a few highlights from the FCC-hh studies, where, of course, not as much work has been done, but there are some very interesting results. So let's start with the top-Yukawa coupling, which you can measure from TT-Higgs. Of course, in a hadron collider, the normalization is much more difficult. So what you actually want to measure is TT-Higgs over TT-Z, which is kinematically very similar. So you can measure this ratio, making use of the fact that the Higgs and the Z decay to BB bar pairs. And then you basically perform a simultaneous extraction of the Z and the Higgs peak in the very boosted region. You need some additional knowledge, but okay, for the FCC, of course, you would get this from the FCC-hh stage. So if FCC-hh performs a precision measurement of the top Z coupling, as we actually discussed earlier in this talk, and also of the B-Yukawa to the level of 1%, you would actually be able to measure the top-Yukawa coupling directly with a 1% precision. I haven't spoken much about QCD in this talk, so I'll just spend one slide on it. So this is a study of the search for anomalous top-gluon couplings in in TT bar production at FCC-hh. So basically here you see limits of the chromatic and chromoelectric dipole moments, comparing reaches for LHC14 TeV to FCC, and you can see there's substantial improvement. And then this is kind of making only use of the cross-section, but the sensitivity really comes from the region of high invariant mass of the two tops. So people have tried to optimize this, and the best precision you achieve if you limit yourself to the region of above 10 TeV. So this is really for the high boosted region. And then finally, a very recent study looking at the production of 4 top quarks in proton-proton collisions at 100 GeV. So this is basically trying to constrain the 4 top operator. So people have actually done a DEF study using the dilepton and then the trilepton final states. And what you see here are single operator limits for FCC-hh from 4 top production versus, for example, what we have seen earlier in the talk, click TT bar production at 3 TeV, and you see actually the limits are not very different. So also for hadron colliders, if you go to the highest energies, you really make you enhance the sensitivity to the 4 fermion operators a lot. On the right, you see an illustration how this actually would compare to other observables in a benchmark composite model, and you see it's actually very interesting. So yeah, so these were just a couple of highlights on the reach at FCC-hh. So there's clearly very interesting measurements possible there. And then I want to conclude the talk with somewhat of an overview of flavor change. So this is just an overview of the current status of the search for flavor changing neutral current top quark decays at ATLAS and CMS. So typically the branching ratios in the standard model are strongly suppressed to the level of 10 to the minus 12 or below. But of course, strong enhancement in certain DSM models is possible and can go up to the levels of 10 to the 5, 10 to the 4 or so. You see in the blue and in the red dots the current limits from ATLAS and CMS. And you see that typically those are on the level of, let's say, 10 to the minus 3, 10 to the minus 4. Now, for the European strategy, we actually made a survey what's available in terms of studies for all the various collider options. So I just want to discuss this a little bit. So here's a table from the briefing book, which basically compares the projections for high luminosity LHC with all the different collider options. And the numbers in this table are on the branching level, branching ratio times 10 to the 5. So just to compare with the previous slide. So of course, the first class of decays is top-2 and the jet. And I've here separated the cases where we have dedicated projections for charm and up separately, or if it's just measured together. And you see, okay, so the high lumi LHC would go down to 10 to the minus 4. And then if you would operate any plus and minus machine above the threshold, you would have in the order of million of top decays, which would be best used to improve the limit on final states with charm in the final state. And then you see also here that, of course, if you have the very high statistics at the FCC-hh, you would gain almost an order of magnitude over the current high luminosity LHC limits. Let's look at top-to ZQ decays. So there's a study for FCC-hh, which basically makes use of anomalous single top production. And then, of course, here we also can set limits in EP collisions. So you see limits from LHEC and FCC-hh. where you can basically use the DIS production cross-section for single top quarks to set limits directly. And you get something which is an order of magnitude better than HL-LHC. And then, okay, again, we have the ultimate reach from FCC-hh, which is based on an extrapolation from HL, and you see you gain, again, an order of magnitude. Top to gamma quark, okay, for the FCC-hh and for the EP colliders, it's basically the same technique as I discussed on the previous slide. So you can use anomalous single top production in E plus E minus, or you can use the DIS cross-section for single top production. And then there are studies for ILC and click using the final state with a charm and a photon in the final state. And then, of course, also there are studies for HL-LHC and for FCC-hh. And FCC-hh is focusing on the boosted regime. And again, we get here almost 2 orders of magnitude improvement. Finally, of course, the top-to-gluon quark decays. Those, of course, are really dominated by the hadron colliders. So far, there are only projections for HL and high-energy LHC. This is using single top production, and okay, we can see the strong gain in precision with the center of mass energy. Let's try to conclude something from this table. Indeed, there's a complementary set of possible measurements for flavor changing neutral current top quark decays in E plus E minus, in EP and in PP collisions. I think it's very clear that not all the possibilities have been explored yet, so there's still a lot of things to do. But generally, improvements by at least 1 to 2 orders of magnitude with respect to HL-LHC seem possible. I want here also to discuss some EFT analysis of flavor changing neutral current effects. So let's start by looking at limits obtained from the branching ratios, from the HL-LHC limits, which you have seen on the previous slides, and also including anomalous single top production limits from lab 2. And then you see in the left the constraints from 2 years ago or so, and then on the right the way it's expected to evolve in the high luminosity LHC area. And then here always the red is for the top up operators, and the blue is for the top charm operators. Let's also look at the energy dependence of this. So this is an EFT study of E plus E minus to top jet at click. And we see the limits on the relevant operators in the plot. It's a bit a complicated plot, so I have to explain a little bit. So the black arrows, which is here, for example, is basically what you can get from here and here, is basically what you can get from studying top quark decays. So definitely those are not competitive with the anomalous single top quark production. The red arrows and the magenta arrows are basically the LHC and high luminosity LHC limits, which we have seen on the previous slides. And then you see in the bars, basically the limits on these operators from top jet production at the various energy stages. And it's basically the same conclusion as we had from previous EFT studies. So especially the 4 fermion operators grow quickly with, I mean, the precision on the 4 fermion operators improves very quickly with the center of mass energy. And if you have a high energy lepton collider, this is much more powerful than reconstructing the top decays. So this is basically the program ahead for this talk. Let me try to summarize. So very clearly, the top quark plays an important role at any future high energy collider. Maybe this has gotten a bit forgotten in the last few years, where we have discussed so much about Higgs physics, but indeed the top is also very crucial. There's a well-defined program for an E plus E minus collider at and above the top pair production threshold. So of course the threshold scan is still the best possible option for mass measurement, with ultimate precision in the order of 50 MeV. And then if you operate the collider above the top threshold, you get an improvement on the top electroweak couplings by at least an order of magnitude. If you go even higher in energy, of course, you get a direct measurement of the top-Yukawa coupling, and it also gives you access to the CP mixing and the TT Higgs coupling. In several examples, we have seen the benefit from highest possible energies, actually in the plus minus anti-hadron collisions for fermion operators. And then for the whole area of top-quark flavor changing neutral current effects, there's a large amount of complementarity between different colliders, so E plus, E minus, EP and PP, and even different energy stages. So I think especially for the highest possible energies, there's still a lot of very interesting things which should be studied, and there's also more processes which could be looked at. So yeah, thank you for now for the attention.
Thank you. Thank you very much, Philipp, for this very, very nice and complete overview of the possibilities at, for top physics at future colliders. So the floor is open for questions or comments. Yes, Roberto, please.
Yes, I have a comment and a question concerning the top-quark, the TZ couplings. You mentioned the possibility to use the final state to measure essentially the polarization of the top in the semi-leptonic channel, but in fact, this for sure it was just the first exercise. You can use all the final states to measure the top polarization. Is exactly what was done at LEP for the tau polarization. Even the hadronic final states can be used. So I'm sure that eventually it will be possible to do much more about that. It is really a very interesting method that it can be used to improve quite a lot of the sensitivity. This is just the comment. The question is there any study concerning that has been done concerning single top production in a plus minus? Even at LEP, we were even producing we produced a couple of papers about that. So it's clearly it is an interesting channel, but I've not seen studies. I'm not aware of studies. Something that has been explored in these preliminary studies.
Right. So let me start with the comments. So no, I fully agree with you, of course. So I was saying single top because this is actually what went into the projections I've shown on the next slide. But you're absolutely right that the other final states have great potential also to improve this and should be studied also. I mean, especially in this very clean environment, very clearly one can do things with the other final states as well. And then for the second question, for the single production, so the only studies I'm aware of are those which I discussed in the part on the flavor change. So for example, here there's a Delphis level study, I think, for FCC-hh for a plus E minus to top plus jet. But,
okay.
And then also the click study, which I think is also Delphis level for top plus jet. But I think this is all which I'm aware of, which was done in the last few years.
Thanks.
Philipp, we did a little paper on single top production, but
excuse me, Marcel, we cannot hear you.
Oh, sorry.
Could you please speak louder or come closer?
Is it better now?
Yeah. Now it's good.
Okay, yeah, we wrote a paper on single top production at E plus E minus, I think 5 or 6 years ago, but it was sort of abandoned beyond that, and we didn't fully take it into account when we did all those EFT studies, for instance. So we know it's there. It was looked at apart from the FCNC studies that Philipp already mentioned. It should be part of the overall program, but we haven't taken it into account fully since then. So yeah, it could really benefit from a bit more study.
Is there also a possibility through WG fusion?
I think this hasn't been looked at, unfortunately.
Okay, Roberto, please.
Hi, can you hear me?
Yes.
Yeah. So I probably missed it while you were discussing it, but this FCC-hh sensitivity to white top, can you remind me if it is coming indirectly or it's a direct test of this coupling?
Sorry, you were talking about the top-Yukawa coupling?
Yes,
Yeah.
yes. I think it's maybe the middle part of your slides.
Ah, yes, yes, okay. And you were asking for FCC-hh or FCC-hh?
Yeah, I was asking for EE alone.
Yes, yes.
I saw some numbers and, well, I don't remember where they come from, so I was asking you if they're indirect reach or maybe it's in combination with something else or it's direct. I just don't remember.
Okay, thanks. Okay, so indeed, if one does an analysis of the Higgs couplings, one can get sensitivity to the top-Yukawa coupling through loops, of course. So, for example, from the Higgs to glu-glu. And indeed, I think the projected precisions for FCC-hh would be in the order of 1%. So, of course, this is an indirect extraction, so it's not a direct extraction, of course. But indeed, there are limits. There are projections in the order of 1% from this type of analysis. Maybe Marcel wants to add something. He has the hand up, and I think he has been involved in this a bit.
Yeah, people have also looked into the threshold scan as a source of a Yukawa measurement, right? It's not quite competitive, I would say, if you take into account the theory uncertainty, the degeneracy with alpha S.
No,
but their sensitivity is there.
Yeah, so I think if I remember correctly, the precisions you get from the threshold are in the order of 10%. If you fit the mass and the top-Yukawa at the same time at the threshold, you don't have a competitive result. That's true. This has been looked at, yeah.
Okay.
Thank you.
So actually, I have a few comments and questions. If there are no other, for the moment, no other hand raised. So I don't know. Could you please go to slide 13, please?
13, yes.
Yeah, when you discuss the 13. Sorry.
13. I'm sorry.
1-3. Yeah. So, yes, yeah, the one before it was 14. Where? No, 12. Then sorry, 12. Yeah. No, well, then it is clear that many computations have been done computing. You see, next to leading order and all that. And then afterward, you basically quote the small error when you include all these corrections that you get from scale variation or MT or alpha S. But the impact of this ISR and radiation loss, the other effects appear much larger than what one would expect from, for example, from next cube correction. Okay, have you also considered variation on the unknown parts related to these other sources of these other corrections? Because
so
yeah, then you have these plots where you vary MT. Yeah,
right. So if we talk about here these energy loss from radiation, so for the Beamstrahlung part, which is basically the Bremsstrahlung in the field of the other bunch at a high luminosity collider. So this is, of course, dependent on the accelerator parameters. So it's very hard to calculate precisely, but you can measure it very precisely with, for example, Baba, large angle Baba events. So this uncertainty has been estimated and is actually not a dominant effect. For the second part of the question, for the ISR part, at the moment I don't think an uncertainty on the calculation of ISR has been included. That's an interesting point.
Okay. Well, also I think before now that I think before this next cube, there is probably also some sort of mixed QCD electroweak corrections that my knowledge is not known, that could be evaluated, I think.
I think this is a valid comment, yes.
Also by people in the audience, probably, but okay. Then if, I don't know, Marcel, you still have your hand raised. Do you have a question or?
Yeah, but I don't, go ahead if you want.
Oh, I have some other considerations, but of course, feel free to interrupt whenever you like.
Okay.
So, well, a curiosity, no, slide 17, just a bit. Yeah, I see that the statistical error here, I don't know, seems the largest component, no? We expect that, I don't know, you as experimentalists will do always better than what you claim, or at least we are now used to think this after the great performance of, at least for the, I don't know, the technical side. And also we as theorists, we expect to make better and better computation. So is this just for this 4,000, this 4 octobarn, inverse octobarn, is this exactly the target of the project, or this statistical error is expected to be reduced? I don't know. It's just for example that you take this number and then the statistical gives the main, because I saw this also in some other slides, that the statistics looks the limiting factors for your measurements.
Yeah. So so here the 1 inverse autobahn for click at 380 and the 4 inverse autobahn for ILC at 500 GeV is what's assumed in the official baseline scenarios for those colliders. So if you look at the official documents for those colliders, it's what's assumed in their baselines. So I know for click there are some studies to improve the luminosity of the first stage, which are currently ongoing. But I mean, I would not expect that this now changes by let's say an order of magnitude or so. There are optimizations maybe to be done, but in general, indeed, for all the plus and minus machines, many of the measurements are limited by statistics. That is true. Yeah. Mm-hmm. And those numbers we use here are basically from the official baselines, what people feel comfortable recommending at the moment. Yeah. But the accelerator experts are also recommending at the moment.
Yeah. To add to that, we have been a bit conservative, I feel, on assuming the reconstruction efficiencies, etc. This is a number that we can definitely do. It's not for some of the other projects. You sometimes see what I would call targets. If everything comes together, we get very lucky, and we have this much better performance in the end, and we hope then you can do it. Now, this is a number that with today's theory, with a nominal integrated luminosity and with conservative assumptions on how well we can do the experimental part, you could achieve these precisions. There's quite a bit to be gained potentially from looking at events with a gluon. But we have much greater statistics there. It's also much more complicated to disentangle which was the gluon and which were the top decay products. But statistics there is much larger. So if you have a student that's interested, we could try, and we were hoping to do this as well, but we ran out of time.
Marcel, something happened to your microphone, I think, but the sense of your point is clear.
Okay, so there is more that we can study, and that there could be significant gains in the gluon channel, I suspect.
Okay, great, thanks. Massimiliano.
Yes, yes, sorry. Can you go back to the slide where you had the threshold scan? I think it was 13, probably. Yeah, no, the next one probably, sorry, the one. Okay, so yeah, so actually, I mean, I have maybe a very naive question due to my ignorance on plus and minus collisions, but which mass do you extract from a threshold scan? So what is this MTPS?
Right, so it's the mass in the PS scheme which is used in the non-relativistic calculation, which is used to template fits to the threshold.
Okay.
But, yeah.
Thanks. Okay, no, that answered my doubt. Okay, thanks a lot.
So as we are measuring a cross section in the threshold region, basically, yeah, what we measure is the mass which is used in the theory calculations.
Okay. Okay.
Massimiliano, right, if you want the MS bar mass, and I think that is what people expect in the end, we can convert with negligible precision, right? Enough loops are known that the precision of the calculation itself is good enough. Now we do have to be careful about alpha S, and there's in fact a little cancellation between the alpha S uncertainty from the measurement itself and the alpha S parametric uncertainty in the conversion. So you could take that as accounted already in the 50 MeV that we usually quote.
No, because I mean my doubt was, I mean, I have in mind also I will say something about it. Very obvious actually about the issues with the pole mass. So I mean, if we have an uncertain ambiguity which is of the order of 100 to 100 MeV, then you tell me that you measure this with 50 MeV, so it's not a pole mass. Okay, good, fine.
No, it's not.
Okay.
And I think the calculation which Marcel mentioned, I think the precision, I mean, the additional uncertainty from the translation from PS to MS bar was in the order of 10 MeV, if I remember correctly.
Yeah, from higher orders, that's 10 MeV.
Okay, so then this is a short distance mass essentially. So it's something can be sort of defined with that accuracy. Good.
Yeah. And the whole debate about the pole mass we'll be able to settle probably once we have that measurement. Right? We can do a template mass measurement at the plus and minus collider if it runs above the threshold with the Monte Carlo that we've always used at the LHC, and get a precise pole mass from there, and then we can see if it was compatible with the masses we get from the threshold scan from the other analyses.
Okay, good.
Thanks. I see Roberto. Please, Roberto.
Just a curiosity after the previous question, previous question. What is the final uncertainty projected that you have in the next slide? I think from the traditional method, the one from TT bar without any radiation. Maybe it's this, maybe it's 2 slides after. So top mass continuum before. So I thought there was something with the final state measurements of TT bar decays, like the same as you do at LHC essentially. not requiring any photon or gluons and studying the spectra of these photons or gluons, but really reconstructing the final states.
Yeah. So here's So here's the here's the example for click at 380. So the statistical precision for hadronic events is 30 MeV, for semi-electronic is 40. But of course, you would have a sizable additional theory uncertainty here from the interpretation, which we have. I mean, you would have similar issues as at the LHC with the interpretation of this measurement, of course, which I didn't dare to put a number on.
Yeah, okay. I don't want to enter into that discussion, in fact, but just to let's say cross our fingers and we know how to interpret that. What would make was essentially asking how better is that compared to the clearer measurement you discussed with TT gamma, and it seems you say 40 MeVs per channel, rather smaller than the other one.
Yes,
but then you mentioned also jet energy scale, which is always there.
Yeah. So here, so for the indeed, so the statistical uncertainty would be, let's say, factor 3 or so better than with the TT gamma method. For the jet energy scale, we haven't done detailed studies yet, but we had a quick look, and it seems you would need to run a few weeks each year on the Z-pole to get a calibration to match the statistical uncertainties.
Which sounds feasible,
but the details would have to be worked out.
Okay, thank you.
Yeah, Philipp Yongping is doing a study where he does gamma Z, and he's got quite promising results, but I'm not sure if the JES, etc., would be sufficiently good that they would not be dominant here. But yeah,
we would have to look at the numbers from that, but that's an interesting thing to look at. Yes.
But yeah, I'm assuming that, right, you'd get a statistical uncertainty that's small. You'd work very hard to try to get the experimental uncertainty small, and then we can start to investigate what the interpretation of a Monte Carlo mass is with those data and the other measurements, and hopefully we work it out and we leave the top mass well understood when we're done.
Okay.
So I mean, all the studies of the jet energy calibration is of course very relevant also for other things. So this definitely deserves more study, let's say. Yeah.
Okay. Roberto, you still have your hand right. I don't know. Something more to add or? Okay. I have a curiosity on slide 38. Because when you, but this is also fine as well, because you have numbers for FCC-hh for gamma C and gamma top and gamma C and gamma U, but not a number for gamma Q. That should be the, is there any special reason for that?
No. So this table is a survey of all the available studies. So if there's not a number in the table somewhere, it doesn't mean it's not possible. It just means.
No, I mean, we can expect a similar performance, right? Because it's just the envelope basically of the two studies. Okay.
So yeah, when making the table, I put separately if there were separate limits for gamma C and gamma U, or when there was a combined limit for gamma Q. But of course, you can combine the two numbers into a number for gamma Q. I didn't do it to make clear that these limits were actually originally obtained separately.
Okay.
And then, I mean, for all the empty boxes, of course, the studies are just missing in many cases.
Okay. It's clear. Thanks. Okay. Further questions or comments? I don't see raised hands. Yeah, Marcel. Want to add something or?
Yeah, very nice overview. I actually learned a few new things. So one of the things I didn't remember seeing before was this comparison of the 4 top production at FCC-hh and click and ILC TT bar production. Now you compare one operator, but I have a hard time seeing which operator is common to these processes, right? The click and ILC study looked at E plus E minus TT bar for fermion operators.
Yes.
And I assume FCC-hh looked at the 4 top contact interaction.
Yes.
So what is CTT and how can we compare these directly?
I think I would have to point you to the publication for this one.
Yeah.
So indeed, they did not. So they did this study for the 4 top production and extracted the operator, and for the click they translated just the paper, the result from the TT bar global analysis, which I showed earlier. But for the exact definition of the operator, I would have to refer you to that publication.
Yeah. Are your slides on the agenda yet? I couldn't find them earlier.
So I will send them right after this.
Okay, then I can find the paper. Okay, thanks.